Okay, so it has started recording. So welcome back. So there was some technical glitch today. I don't know how, but anyway, I think it's sorted out. So today is lecture 7. What we will do today is the global Cauchy theorem. We have done a lot of groundwork, so it's not very difficult. As usual, we will follow Rudin. So that's all that we will do today. And so let me just, finish the math part continuously. I think taking a break in between, we are losing a lot of time. So we will finish what we want to cover and then stop and then discuss. So in the discussion session, you can ask me questions either based on the syllabus, the math part, or some other things about quizzes, assignments. I think many of you are not very happy with the grading, so you can ask me. Okay. There's a reason why the grading was a bit tough. So you can ask me, I will frankly tell you. Okay, so what did we do last time? Last time we did open mapping theorem. And I hope you are all going through the slides and also the book. Okay, I am following the book line by line. So we are following Rudin. Please do follow the book and also go through the slides. Amanpreet, you wanted to say something? Amanpreet?
No, sir. No, sir.
Okay, fine. Yeah. So last time we did the open mapping theorem. If you recall, though the main point was open mapping theorem, it came as a corollary to something else that we proved. So open mapping theorem would say that holomorphic function on a region is automatically open. It takes open sets to open sets. As preparation, we did inverse function theorem. And I call that theorem not inverse function theorem, but we added a little bit more, and I might have called it towards open mapping theorem, towards OMT. So what was the point? Inverse function theorem would say that if there's a point, holomorphic function is given. If there's a point at which the derivative is non-zero, it's a local theorem. So if there's a point at which the derivative is non-zero, then there is a neighborhood of that point on which the function is first of all injective. And you can also show that throughout that neighborhood derivative is non-zero. Derivative is given to be non-zero at a point to you. And then you will pick a neighborhood and you will show that it's injective there and the derivative is non-zero throughout that neighborhood. And then you show that if V is that neighborhood, then f of V is open. Right? You showed that f of V is open. And if you take any sub-neighborhood of V, there also all these conditions are applicable. So you're actually showing that f is an open map on V. Any open subset also the image is open. And then you consider the map to its range. So by definition, it is onto. So it's a bijection from V to its range, and therefore it's invertible. And we showed that the inverse is holomorphic. How did we show that the inverse is holomorphic? We actually had a formula for the derivative of the inverse. Derivative of the inverse was 1 by the original derivative at the correct point. Okay. So this is what we proved. And then we proved another local theorem. So our first observation was if you take power maps, they are automatically open. Power maps are open maps. This was an observation. And then we noticed that if you take two open maps and if you compose, the composition is open. And therefore, we noticed that if there is a function whose derivative is not vanishing, and then if you compose with the power map, that's open. And then we proved a local theorem that any holomorphic function locally is of this form, up to addition by a constant. Locally, it's of the form pi m composed with phi, where phi has all the nice properties as in towards OMT. So phi prime is non-vanishing, phi is injective, etc. All these nice properties. Moreover, in this local theorem, we manufactured a V such that its image is actually an open disk D0R. And then we proved open mapping theorem as a corollary to this theorem. So this is basically what we did. And let's go to global Cauchy's theorem. So let's recall once again on the slides, and then we will go to today's lecture. So let me share the screen. Yeah, I hope you can see the screen. Can someone confirm?
Yes, I can see the screen.
Yeah, so I hope everyone can see the screen. So let's, so lecture 7, today's topic is global Cauchy theorem. So we are not doing much today. I thought we can discuss a bit more if there's time, but we started late because of the technical glitch. So there are many messages on WhatsApp. So is Chirag here? Chirag has joined here? No. So I think whoever started the general meeting, please end that meeting. I think some people are finding it tough to join here. Okay, Ariman is responding there. So, okay. Rahul?
Yes,
Rahul, can you just unmute?
sir. Yes, sir.
Did you start that meeting in general?
Sir, by mistake I done, sir.
Yeah, so can you go there and stop that meeting?
Yes,
End
sir.
that meeting? Yeah, please end that meeting, yeah. Okay, so let's come back to the slides. This much we recalled. In the last class, we discussed the inverse function theorem as towards open mapping theorem. In the sense, not just the standard statement of inverse function theorem, but we had this, the map is open also we proved. And then proved the open mapping theorem. IFT is a local result, a point at which the derivative doesn't vanish, has a neighborhood where the holomorphic function is bijective onto its range, of course, and the inverse is also holomorphic. In fact, the derivative of the inverse is inverse of the derivative, formulated appropriately, meaning, inverses on some other domain. So you are taking a point which is the image of this point, etc. So if H is the inverse, then H prime W is 1 by F prime Z, where Z and W are mapped to each other. This was also towards OMT because we proved that such a map has a non-vanishing derivative throughout this neighborhood, and on that neighborhood it's an open map also. In fact, we used this much to show that the power map is open, and then we proved a local result which said that any holomorphic function is locally a nice function with properties as in the earlier theorem. So phi is open on a neighborhood, phi prime is non-zero, and all these things. Okay, and we could choose our neighborhood V such that the range is not just any open set, but actually an open disk composed with a power map. So such a nice map composed with power map, and that nice map, its range is actually an open disk. As a corollary, we saw that as a corollary, we proved the open mapping theorem. And as a corollary to this proof, we also saw that an injective holomorphic map has derivative non-zero everywhere. Why is that? Because if derivative is zero at a point, then you can consider the function f minus z naught, where z naught is a point where derivative is non-zero. So f minus z naught has a 0 at z naught, and its derivative is also 0 at z naught. So it has a 0 of order at least 2, and therefore from the proof it follows that it is at least 2 to 1, contradicting injectivity. So injective holomorphic map has derivative non-zero everywhere. And we also saw that the converse is not true, like e power z. Its derivative is e power z itself, and therefore e power z derivative is non-zero everywhere, but it's not, it's periodic, it's not 1, 1. It's locally 1, 1. So today we will discuss the global Cauchy theorem. So Cauchy theorem is basically saying that the integral of a holomorphic function is 0. We have already seen this statement, right? We saw this statement on any region. So up to now we have seen statements where we put some restriction on the region or some restriction on the curve. So we proved Cauchy theorem for triangles where omega was anything, no restriction, but the curve was, the path was boundary of a triangle, so some restriction on the path. Then as a corollary to this Cauchy theorem for triangles, we proved Cauchy theorem for a convex open set. So here the curve, the path gamma can be anything, but your domain was convex. Okay. And now we are going to prove a general Cauchy theorem. Of course, there will be some topological restriction, but we will see. Okay. But it's much more general than what we have done. Those were local statements, and this is a global Cauchy theorem. So omega will be any region, and the curve, the path has to satisfy one property, and then the Cauchy theorem can be proved. That's what we will do today. And of course, you know, as an application of Cauchy theorem, we had proved the Cauchy integral formula. In fact, our proof, we will prove the Cauchy integral formula first, and then Cauchy theorem will follow. So both will be proved together. So we can do a bit more. You know, we don't need a closed path. We can also consider sum of closed paths in order to do this thing. So we will introduce some terminology. So let gamma 1 etc. gamma n be paths in omega. So by a chain we mean a finite formal sum of paths. So capital gamma is a chain. That just means it is gamma 1 plus etc. plus gamma n. For some paths it's a formal sum. So this plus doesn't mean anything. It's just my notation. Okay, there is nothing called a plus here. It's just my notation. What it really means is the following. I can define integral there, and by now already we know we have done path integrals. You know, if you take two things you can add, like right on the triangle, what was the meaning of the path integral on the triangle? We added it on the sides. So similarly, integral f z dz on this gamma, when gamma is a formal sum of paths, by definition it is on each path you take the integral and you sum it up. Okay, so this is the definition. A cycle, so I say that a chain is a cycle if each of the gamma is closed. So a cycle is a sum of closed paths. And Rudin's notation, if you put a star, it's the image, right? Gamma is a map from some closed interval to C, and you take the image. What you see in C, that's gamma 1 star. So gamma star is the union of all this. So if gamma is a cycle, and if alpha is not in gamma star, alpha is not in the range of, alpha is not in the image of these paths, then we can define the index of alpha. What is the definition of index? It's 1 by 2 pi I integral over dz by z minus alpha. Okay, and the integral is over gamma now. And the integral over gamma, you know what it means. It's a sum of integrals over each gamma I. So index of alpha with respect to gamma makes sense. And of course, index of alpha with respect to gamma is nothing but summation of index of alpha with respect to gamma I, as you can see from the definition of the integral. Just from the definition, this follows. Okay, so we have the notion of index of a given number, a given point with respect to a cycle. Okay. Now you can put an equivalence relation. You know, we are going to put an equivalence relation on cycles, because if on two cycles, if I'm getting the same integral, then I say that those two are equivalent. So I will say that gamma 1 plus etc. plus gamma n is same as delta 1 plus etc. plus delta k. Is there a question? Surya, you have to mute. Lot of disturbance. Yeah, please be careful. Sometimes there's no disturbance even if someone unmutes, but sometimes there is. So unless you want to ask a question, you keep it muted. That will be better. Okay, so we say that two cycles are same if the integrals, you can integrate on the first chain and you can integrate on the second chain, and if the integrals coincide, for every continuous function on this images, right? If you consider the union of all these images, then both these integrals make sense. And suppose they are equal for all continuous functions, we say that these two, I don't distinguish between these two chains. Okay. In particular, observe that a cycle may be a sum of paths that are not closed under this equivalence, right? So if you take a circle, that's of course a cycle, but it can also be, you can take any point and you can take it as this arc plus that arc. So we are saying that these two are same for us. I mean, up to this is an equivalence actually. So we are saying that these two are same for us. So a cycle may be a sum of paths that are not closed. That's okay. And now we are going to introduce a definition. So observe carefully what the definition is. A cycle gamma in omega. So omega is some open set, and you have a cycle, and it is said to be homologous to zero in omega. Homologous to zero in omega. Maybe the underline should have gone up to in omega. The definition is homologous to zero in omega. It depends on omega. If So it's in terms of the winding number. If the index of alpha is 0, index of alpha with respect to gamma is 0. And what is alpha? This should be true for each alpha outside omega. Is the definition clear? You're taking a cycle in omega and you are defining homologous to 0 in omega. And the definition is the winding number, the index of alpha with respect to gamma is 0 for every alpha outside omega. So take a simple example. Take the unit circle, and suppose omega has no puncture inside the unit circle. Okay, suppose you take the whole complex plane, for example, there's no puncture or anything, and if you take the unit circle, what is the index of alpha with respect to gamma? If you take the whole complex plane, of course there's no alpha, so vacuously it's true. Now suppose you take a disk, so that it's not the whole of C. So if you take alpha outside omega, it's outside a disk. So index of that point with respect to a circle inside the disk is of course 0. So it is homologous to 0. But suppose there's a puncture inside the circle, then you can choose alpha to be that puncture. It is outside omega. In which case index of course is non-zero, right? It depends on how many times you wind, index may be that number, positive or negative, whatever. Anyway, it's not 0. So a circle surrounding a puncture is not homologous to 0, and otherwise it is homologous. So this is the definition of homologous to 0. Okay, and now we can state the global theorem. Let omega be any open set, and let F be analytic throughout omega, holomorphic throughout omega. And if gamma is a cycle in omega, that is homologous to 0 in omega. Okay, so we just recall the definition. And if gamma is a cycle that is homologous to 0 in omega, then first we are going to prove the Cauchy integral formula. So Fz times the index of z with respect to gamma is 1 by 2 pi I integral over gamma Fw dw by w minus z. Okay, so this is the standard Cauchy integral formula form. The generalization here is we are proving it very generally. Omega is open, gamma is also a sum of paths, and that also is quite general. There's only one condition, it is homologous to 0. We are not restricting it like the boundary of a triangle or anything. It's much more general. Any funny shape is okay. Only condition is homologous to 0, and then we are proving the Cauchy integral formula. And once we have the Cauchy integral formula, of course Cauchy's theorem will follow. So this is defined whenever z is outside gamma star, only then this makes sense. You want w 1 by w minus z to make sense, so you put this condition. This is true. And of course, integral fz dz is 0 if f is holomorphic. That follows from the Cauchy integral formula, because you can take capital F to be z minus 8 times f of z and apply the Cauchy integral formula to that function, and you will get this to be 0, because capital F of a will be 0, right? So this follows from that. So we are going to prove this. This is what we have to prove. Is the statement clear to all of you? So omega is any open set, there is no restriction, and gamma, only one topological restriction is there, that it should be homologous to 0. It's a cycle, it can be finite sum of closed paths. So it's quite general, and this is general Cauchy's theorem, global Cauchy's theorem. Okay. So both Cauchy integral formula and Cauchy's theorem, we are putting it together, and the Cauchy integral formula form is what we are going to prove first, and this is an immediate corollary to that. Okay. So the proof that we are going to present as, all our proofs are from Rudin, but here what I am stressing is this proof is from Rudin 3rd edition. The first 2 editions had a more complicated proof, and by the time 3rd edition came, there was a new proof. See, we are doing classical complex analysis. Most of our results are not from the 20th century, but even before. So by relatively new, I mean something in the latter part of 20th century. So this proof was discovered in 1971, and this is due to a mathematician called John Dickson, and the proof is from 1971. So when this proof came, it's quite an elementary and elegant proof. So Rudin in his 3rd edition removed his earlier proof and put this proof. So it's quite beautiful. And earlier proofs of global Cauchy's theorem assumed, some more complex analysis. For example, I think Rudin makes I did not look at that proof or a previous edition, but he makes a note that his previous proof used Runge's theorem, which is yet to come, right? So this proof is elementary. Whatever we have done till now is more than enough. So we will do this proof. So if you remember the proof of inverse mapping theorem, not inverse mapping theorem, right? Inverse function theorem. What was the starting point? We considered a particular function g, a function of 2 variables, and I asked you to check it is continuous, right? And then we used that in order to get a kind of inequality. From that inequality, one-oneness was automatic, that the function is one-oneness was automatic on a neighborhood. We could manufacture a neighborhood. Neighborhood came from the continuity of that function, and you got an inequality on a certain neighborhood, and one-oneness was automatic, that the derivative is non-zero throughout there was also automatic. So the crucial point was continuity of this particular function. Here also it's the same function. It is a continuity of this function, that's a starting point today also for global Cauchy theorem. Okay, so you take this function and right, you remember this function, right? Even in the proof of our local Cauchy integral formula over a convex set, we use this function, but it was a function of one variable. This part you fix and consider it as a function of z alone, and then the continuity of this is obvious, and this is what we used. Let me ask you, consider this as, because it's going to come in our proof later. You remember this, right? When we proved a Cauchy integral formula for a convex set, we considered a function on omega defined by g of z equal to, bracket you close here, by you take some other point and define it like this. For w not equal to z like this and w equal to z like this, then of course continuity is automatic just from the definition. Limit as w goes to z by definition is this. So this is continuous. One variable continuity is obvious almost by definition. And then, we had proved Cauchy's theorem for a convex set under the assumption that if your function is continuous throughout and holomorphic, maybe except at a point. One exception was allowed, and then we had proved Cauchy's theorem. And then we could, substitute this function and apply Cauchy's theorem. That was the proof of Cauchy integral formula. We could apply this because, it is differentiable at z equal to w is not all that obvious, certainly not at that point, at that time. Later it became obvious for us. Okay, and that's what we use. So continuity throughout and differentiable, perhaps with one exception, 1 point exception. So this I'm just recalling. But now we certainly know that this function of one variable, okay, g of z equal to defined like this, is of course differentiable also at z. Can someone quickly tell me why? We have done this already. It's just recalling. Function of one variable on omega defined like this. Of course, it's continuous, but it's also differentiable at that point. See, everywhere other than w, of course, it is clear, but at w also it is differentiable. Why is that?
We had seen that even when we keep one possible exception, it turns out to not be an exception later on.
Yeah, and this followed because of Cauchy integral formula, right? With the exception, we proved Cauchy integral formula, and or even before Cauchy integral formula. With the exception, we proved the Cauchy theorem, and we got an antiderivative. Yeah, then maybe after proving Cauchy integral formula, we had this corollary that derivative of a holomorphic function is derivative. So exception was only in our mind. There's no exception. That's one proof. But Ariman, can you think of one more proof? Just the continuity is enough in order to conclude differentiability at that point.
The removable singularity theorem.
Removable singularity because Riemann's theorem. So if you have boundedness, then the singularity is removable. So this singularity is removable because it's continuous, so it's bounded. But anyway, so this we're just recalling. That's not what we are doing. What we are doing is this is continuous as a function of two variables, which I had asked you to check, and it's there in Rudin. So I assume you have checked that. So it's continuous on omega cross omega. This is our starting point. And therefore I can define this thing. This makes sense, right? This is continuous in both the variables, in particular in the variable w, and therefore the integral makes sense, right? If you have a continuous function, you can integrate, and gamma is a sum of closed paths, and on each path you will parameterize and integrate. So continuity is enough, for you to do the one variable integration. So everything is okay. So you have got a function h. Okay, is the definition clear? I'm using the second variable w, and because of the continuity everywhere, in particular continuous in w, and therefore I'm defining it to be this integral and integrating with respect to w, so therefore it's a function of z. So on omega I have defined a new function. Now I told you that we are going to prove the Cauchy integral formula. Cauchy integral formula will say that integral of fw by w minus z is the index. Fz times the index, but Fz times the index is Fz times the integral of w minus z. So in order to prove Cauchy integral formula, what do you have to prove for this h? See, gzw, you look at the definition of gzw, it has the correct thing, fw by w minus z minus fz times 1 by w minus z. That is the index when you integrate. So in terms of h set, what do we need to prove? Someone tell me. Omkar, can you tell me what do we need to prove in terms of h? Yeah, maybe Ariman. Ariman, are you there?
Yeah, I'm there, but
Okay, fine. Yeah. So, okay, if you're thinking, let's see once again, GZW, right? GZW is this thing, FW minus FZ by W minus Z. We want to show, okay, so maybe you have forgotten the theorem. Theorem is this, right? FZ times the index is integral of FW by W minus Z. But what is index? Index is integral, the same integral over FZ by W minus Z. No, integral over 1 by w minus z. So fz is constant with respect to integral of dw. So it is integral fz by w minus z dw. Take it to this side. So fw minus fz by w minus z, integral over gamma. But that's his function g, no? That's his function g. So what do we need to show about h? We have to show that h is identically 0, right? You agree? If h is identically 0, then plug it in the definition
yeah.
of, yeah. So we just need to show that h is identically 0. Omkar, are you okay with this?
Yes, sir, yes.
See, this is one problem with slides, because not everything can be in one slide. So unless in the classroom on the blackboard, you would have seen the formula on some other panel. So this has to be in our mind, unfortunately. It's okay. But there's nothing here. It's just obvious. But the formula was on the other slide. So maybe, you took more time. So we need to show that h is identically 0. This is what we are going to show. So it's a very beautiful proof. what we are going to show is standard argument. We have used it before. We are first of all going to show that this H is analytic. So first of all, we will show that this H is continuous. Nothing is clear now. We have just defined H. It's well defined because of the continuity of G. First, we will show that H is continuous on omega. Then we will show our standard technique using the local Cauchy theorem for triangles plus Morera. See, once you get continuity, one way to prove holomorphicity is Morera. So Morera would say that, you show that integral over triangles, boundary of triangles is 0. And integral over boundary of triangles we will 0 by using this definition, by interchanging integrals and using Cauchy's theorem here. Okay, so we will show that H is holomorphic. But wherever H is defined, that's on omega. Now I will extend this function H analytically throughout C. That's the technique of this proof. That's where the ingenuity in the proof comes. So we will show that H is holomorphic throughout omega, and I will extend this H holomorphically throughout the complex plane. In other words, there is an entire function which restricts to H on omega. And then we will show that that function is bounded. The entire function that we have constructed, the way we have constructed, we will show that it's bounded. So you have a bounded entire function, therefore by Liouville, you will say that that's a constant. So if you have a constant function, to know what that constant is, you just need to evaluate it at one point. And at one point, we will evaluate and show that it is 0. And therefore, it's a constant function 0. That's the argument. Okay, so let's fill up the details for this argument. So I need to show that H is holomorphic throughout omega. Then I need to extend it as an entire function on C. Then I need to show that it's bounded and therefore it's a constant. Evaluate the constant to be 0. Therefore, H is identically 0. This is the proof. So first observe that. So we are going to show that this function H is continuous. Okay. First point is it is continuous. So observe that if Zn converges to Z, consider a sequence of points Zn and a point Z, so that Zn converges to Z, then of course GZnW converges to GZW. Why? Because G is continuous in both the variables, in particular in the first variable. I mean, not just G is continuous on both the variables. What I mean is, as a function of both the variables, G is continuous. As a function of two variables, G is continuous. In particular, it's continuous in the first variable. So this is obvious from continuity. But I'm going to claim that it is uniform. So this continuity is uniform continuity. So the delta that you choose will not depend on W. So it's uniform across omega. Okay. So why is that? Essential point is, that continuity is automatically uniform continuity on some nice subsets. No, if you have a function which is continuous on a compact set, then it is uniformly continuous. So that's what we are going to use. So on any compact subset of omega cross omega, automatically G is uniformly continuous. We are showing that this convergence is uniform convergence. That's what we have to show, right? N varies, and I'm going to say that beyond a capital N, so maybe I earlier said delta, what I meant is capital N, beyond a stage, this difference can be made arbitrarily small, and that stage usually would depend on this W, but it can be chosen without depending on W. Uniform convergence. That's what we need. So, it follows because you have uniform continuity on any compact subsets, and in particular, you can consider this compact subset. You consider all these points Zn together with the limit point Z. So that forms a compact subset, no? It's a compact subset of omega, and gamma star is also compact because gamma star is union of small gamma stars, and each gamma star is compact and it's a finite union. So finite union of compact sets is compact. So you can consider this compact subset of omega cross omega, and therefore on this G will be uniformly continuous. In particular, given epsilon, there is a delta such that mod Zn minus Z is right? You can take points here. So you could have taken points like something from here. So you can take one ordered pair and another ordered pair, and the difference less than delta implies this less than epsilon, and delta not depending on the points chosen. In particular, I am taking, the same y coordinate, same w. Therefore, the modulus is just mod zn minus z. The other part is not contributing. Less than delta implies gzn w minus gzw less than epsilon. The point is delta is independent of w because of uniform continuity. And now you can choose a stage n such that n greater than or equal to n implies Zn minus z is less than epsilon, right? Zn converges to z. So for this delta, you choose n. So if n is bigger than or equal to n, you have this less than delta, and therefore this you have. Therefore this convergence is uniform. Okay. This is the first observation. And once you have uniform convergence, so recall this was the definition of h. H was 1 by 2 pi I integral gzw dw over gamma. Now gzw is what? It is limit of as n going to infinity of g of zn comma w, and that convergence is uniform. So therefore hz is 1 by 2 pi I integral gamma limit g zn w, but the convergence is uniform on gamma star. So I can interchange. So integral of the limit is limit of the integral, right? Limit of the integral. So limit of integral g zn w. But what is integral g zn w? By definition, it is h of zn. Okay, that was our definition of h of z. So you are getting hz equal to limit n going to infinity of h of zn. So that's what you have to show that h is continuous, right? If Zn converges to Z, then Hz then converges to Hz. That's what we have shown. So because of uniform convergence, you can interchange, and therefore h of Zn converges to h of Z, and therefore h is continuous on omega. Now you have constructed a function which is continuous on omega. Now I want to say that it's holomorphic. In order to show that it's a holomorphic because it is continuous, by Morera, it's enough to show that you take any triangle, you take boundary of that triangle, and you show that the integral is 0. So if you take h and if you integrate on the boundary of a triangle, so integral boundary of a triangle hz will be boundary of a triangle, integral over boundary of a triangle, integral gamma. Now boundary of triangle gamma, these are compact sets. So once you are on compact sets, much more generally, actually you know that integrals, interchanging of integrals in a double integral, interchanging of integrals is okay under certain conditions, not always. What is the theorem called? Can someone tell me? There is a theorem which justifies change of interchange of integrals under some conditions. What is the theorem called? Fubini's theorem. So Fubini's theorem is applicable because in particular, we are on compact subsets, so everything is okay here. So Fubini is okay. So you are getting integral over boundary of triangle, integral of gamma. That can be interchanged. It will be integral of gamma, integral over boundary of triangle. Now integral over boundary of triangle gzw as a function of z is 0. Why? Integral over boundary of a triangle of g of zw dz is 0. Right, on the triangle we are integrating with respect to z. So on the triangle, on the boundary of triangle, integral gzw dz is 0. Why is that?
Because for a
fixed w, gzw is differentiable in z, we already recalled. It follows either from Riemann removable singularity theorem or from generalities that we have seen earlier. Therefore, Cauchy's theorem applies, and that is 0. So what we are showing is integral of hz over boundary of any triangle is 0. Therefore, by Morera, h is holomorphic. So appeals to Cauchy's theorem for a triangle and then to Morera's theorem to conclude that h is holomorphic. Here we have used Fubini as well as the observation that gzw is differentiable in z for a fixed w. I hope everything is clear till now. So we have constructed a function h using the function of two variables g. And we have shown that it's continuous. Moreover, it is holomorphic throughout omega. Now I'm interested in extending it as an entire function throughout C. So for that, I'm going to define a new set omega 1, which is all those points in C whose index over all those points whose indices with respect to gamma is 0. So you have a gamma given, so there's no function here. You have a cycle gamma given and choose all those points Z such that index of Z with respect to gamma is 0. Try to visualize this. So if gamma is just a circle, suppose gamma is a unit circle, what are the points in omega 1? Everything outside the disk, right? So circle will be the boundary of a disk. Any point outside, of course, index is 0. Right? So you're constructing such a set, omega 1. So, if you were only on a disk, you are expanding it to the whole of C. So, you want to consider all those other points. So you are taking all those points in C such that the index is 0. And we are going to make the assumption. See, up to now we haven't used the assumption, the hypothesis that is given that the curve gamma is homologous to 0 in omega. And therefore, what can you say? What is homologous to 0? If you choose alpha outside omega, then the index is 0. So that is what is given to you. Therefore, outside omega, the complement of omega by definition of omega 1, complement of omega is contained in omega 1. That is the hypothesis given to us. Agree, no? What is given to us is index is 0 if alpha is outside omega. Therefore, outside omega is contained in omega 1. That's how we defined omega 1. So C minus omega is contained in omega 1. And you can consider C minus gamma star. That's a union of its components. And the unbounded component is also contained in omega 1, right? When we define the winding number, we have proved that winding number is integral valued, integer valued, and it's actually constant on components. And we also showed that in the unbounded component, the index is 0. So unbounded component of each of this gamma star will be union of small gamma star, and in the unbounded component of each of this, so that will be the unbounded component of capital gamma star, there also the index is 0. This is a property of winding number. It was obvious because integral winding number has the term integral dw by w minus z, and z is going to infinity, right? So you can take z large enough so that the integral is 0. Denominator is increasing, so the integral is 0. And component, it's a constant, therefore everywhere it's 0 in that component. So the unbounded component is also contained in omega 1. So indeed, this is the reason. So now I'm going to define h1, a new function on omega 1. And what is my definition of h1? My definition of h1 is 1 by 2 pi I integral over gamma fw dw by w minus z. This is on omega 1. Okay, so let's define this. Everything is okay, right? Well, what are the points z? It should be defined. So 1 by w minus z should make sense. So this is defined whenever z is outside gamma star. Whenever z is outside gamma star, this makes sense because this is continuous. This 1 by this will be continuous. So you can integrate a continuous function. So this is the definition, and the first observation is h1 equal to h, where h is defined on omega, h1 is defined on omega 1. So what's the meaning of equality? If you have a function defined on one set and another function defined on another set, what is the meaning of saying these two functions are equal? They are equal on the intersection if there is an intersection. So h1 equal to h meaning h1 equal to h on omega intersection omega 1. There may be an intersection, no, of omega and omega 1. So on omega intersection omega 1, h1 equal to h. Why is that? Because what is h? H is integral of gzw. But what is gzw? It is fw minus fz by w minus z. Whereas h1 has only the first term, fw by w minus z. H is fw minus fz by w minus z. So both are same, meaning the other part is 0. That means the index is 0. So on omega intersection omega 1, of course the index is 0 because omega 1, that was a definition. Omega 1, the definition is index is 0. So therefore h1 equal to h on omega intersection omega 1 by the definition of the set omega 1. Agree? Because h will have fw minus fz, h1 has only fw. So h1 equal to h meaning integral of fz by w minus z should be 0. That means integral of dw by w minus z is 0. That means index is 0. But omega 1 has all those points where index is 0. So by the definition h1 equal to h. And h1 is of course a holomorphic function, right? Because anything that is defined, we had this general theorem, anything which has a dw by w minus z kind of thing, it is representable by power series and therefore it's holomorphic. So h1 is holomorphic on omega 1, h is holomorphic on omega, which we already saw. So h is holomorphic on omega, h1 is holomorphic on omega 1. Not only that, these two holomorphic functions agree on the intersection. Therefore, I can define a function phi on the entire complex plane by, if z is in omega, it is hz. If z is outside omega, it is h1z. And this is well defined. This is well defined because on the intersection they agree. So therefore, there is no problem. And this is an entire function because both these functions are analytic. This is holomorphic in omega, this is holomorphic in omega, and on the intersection they agree. So wherever it's defined, it's holomorphic. So this is well defined, and h1 equal to h on the intersection, and therefore phi is an entire function as both these functions are holomorphic. All of you are with me? So you've got an entire function. Now I'm going to claim that it is bounded. In order to show that a continuous function is bounded, one way is, if we know that the limit as z going to infinity is 0, if we know that limit z going to infinity of phi of z is 0, then of course phi is bounded, right? Because phi is continuous. Because if limit z going to infinity of phi of z is 0, then outside a big enough disk, phi z can be made, phi z is bounded because it is going to 0. So outside a disk, it is bounded. Inside a disk, it is bounded by extreme value theorem. On a compact set, a continuous function will take maximum. So therefore, this is all that we need to show. So limit z going to infinity of phi of z, what is it? The definition of phi of z is hz in omega and h1z outside omega. But as z going to infinity, you are outside omega, no? As z going to infinity, no, I'm not saying it is outside omega. I'm saying that if z going to infinity, you're certainly in omega 1, not outside omega. I'm saying that you're certainly in omega 1. Why is that? Because z going to infinity meaning you are in the unbounded component of gamma star, and the unbounded component is contained in omega 1. So as z going to infinity, you are in omega 1, and omega 1, the definition of phi is h1. Therefore, this is limit z going to infinity of h1z. But looking at the definition of h1 as z going to infinity, right? Everything is on a compact set. So these things are kind of fw, and this w will have, maxima, minima, etc. So as z going to infinity, this is limit is 0. So because it's in the denominator and increasing, so this will decrease. So limit is 0. So this is true, and this limit is then 0 by the definition of h1, the formula for h1. Therefore, phi is bounded because limit is 0. So outside a big enough disk, it is bounded. Inside the disk, anyway, it's bounded by extreme value theorem. By Liouville, phi is a constant, and since the above limit is 0, this constant is 0. Right? In the unbounded component, the value is 0, and therefore this constant value is 0. Is that clear? I'm not saying that phi, I haven't shown that phi is 0. I only said that the limit of phi is 0. Limit z going to infinity of phi is 0. and phi is a constant. So if phi, therefore phi has to be the constant function 0, because any non-zero constant, the limit is that non-zero constant. So because limit is 0, that phi has to be constant function 0. And that's what, therefore phi is identically 0, and therefore h is identically 0. Okay, so it's a beautiful proof. Proof is kind of new. It's a 1971 proof. Okay, so this shows that this shows what we wanted to show. I will introduce one more technical term which you might have seen. How many of you had a course in algebraic topology? MSc elective algebraic topology. So Chirag and Aryaman might not have had, but all others had already a course in algebraic topology. I forget which semester it is taught.
Start in this semester. Like it's an elective in this semester.
That is for you, but for MSc students, I forget whether it is there. It has to be
third semester.
So it is going on now. No, how many of you are taking that course, algebraic topology, among the MSc students? How many of you are taking algebraic topology? Can you quickly tell me? Those who are taking it, just say yes. Unmute, say yes. Nobody is taking that course? Mamta, are you taking algebraic topology?
No, sir.
No, Aryaman, what were you saying? You are taking?
I'm not taking the course, but I'm doing reading about it.
And you are also attending the lectures?
No, I'm not taking the course.
Not taking as in the sense you are not crediting it, but are you just sitting through?
No, I'm not taking the lecture either. I'm just reading under a professor.
On your own. Okay, good. Anyway, so yeah. So those of you who are looking at it might have seen, or even in general topology course, you might have seen. This is something basic. Okay, before that I forgot some corollaries. So the CIF part of global Cauchy theorem is what we proved, and second part follows by taking capital F to be z minus a times fz, right? So this is also holomorphic, and if you apply Cauchy integral formula to this, then to capital F, then it follows that integral of fz is 0. So that's obvious. And another corollary is that if gamma 1 and gamma 2 are cycles in omega, such that the index of alpha with respect to gamma 1 is equal to index of alpha with respect to gamma 2, then we can conclude, for every alpha not in omega, then we can conclude integral of f over gamma 1 equal to integral of f over gamma 2. Why is this a corollary? Because you can take the new cycle, which is, so to say, gamma 1 minus gamma 2. What is the meaning of gamma 1 minus gamma 2? That meaning you take gamma 1 and you adjoin gamma 2, but with the opposite orientation. And then index of that new cycle of alpha will be 0. That means that cycle will be homologous to 0. Therefore, by Cauchy's theorem, index over gamma 1 union minus gamma 2 fz dz is 0. But that means integral over gamma 1 is integral over gamma 2. Okay. So if gamma 1 and gamma 2 are such that they are indices of alpha, for every alpha not in omega, if they agree, then the integrals are same. Now a small algebraic topology notion. So if you have any topological space, and suppose you take two curves in X, gamma 1 and gamma 2, a curve again meaning from open interval 0, 1 you have a continuous map to the topological space X. Our X will be omega, a region in C. And these are said to be homotopic in X, or X homotopic, if one of the curves can be continuously deformed to the other without going outside X. Within X, it can be continuously deformed. Meaning, there is a continuous map on the square H from the unit square to X such that H of S0 is gamma 1 S, right? You are starting at gamma 1. So you have two variables S and T. At time 0, T is time. At time 0, you are the curve gamma 1. And the final time, at time 1, you are the curve gamma 2. If this happens throughout S, then you are continuously shifting gamma 1 to gamma 2. And you will say that these two are homotopic. If gamma 1 and gamma 2 are closed curves, that's what we are interested in. We will also demand that H should also be closed. This continuous deformation also should be via closed curves. Okay, then we will say that they are homotopic. That means h of 0t equal to h1t for all t. So all these curves, at every time the curve is closed. Now we say that a curve gamma is said to be null homotopic. This reminds me, homologous to 0 is also called as null homologous. Null meaning 0, right? So homologous to 0, some people say null homologous. And we say that gamma is said to be null homotopic if it is homotopic to a constant path. So if it is homotopic to a constant map is also a curve. And these two curves are homotopic. Gamma and the constant map Z1, let us say, is homotopic. Then we say that gamma is null homotopic. If X is connected and if every closed curve is null homotopic, you say that X is simply connected. This is the definition of simply connected. X is connected. Moreover, every closed curve is homotopic to a constant curve. Then X is said to be simply connected. And we will just prove a lemma, and then we will continue in the next class. If gamma 1 and gamma 2 are two curves, closed paths, path meaning what? Piecewise differentiable, not just a curve, but it's also piecewise differentiable, piecewise continuously differentiable, such that suppose you have this strict inequality. We are going to make use of this technical lemma. So it's an observation actually, interesting observation. Suppose you know the difference between gamma 2 and gamma 1 is strictly less than alpha minus gamma 1 for some complex number alpha. Suppose you can choose an alpha such that the distance between gamma 2 and gamma 1 is less than alpha and gamma 1. Then this is happening throughout. Okay, for all s between 0 and 1. Then the index of alpha with respect to gamma 1 is equal to the index of alpha with respect to gamma 2. So if this technical condition is met, then this is automatic. Index of alpha with respect to gamma 1 is index of alpha with respect to gamma 2. If there is some complex number alpha such that the distance between alpha and gamma 1 is strictly bigger than the distance between gamma 2 and gamma 1. Let's see a proof. This we are interested in because in the next class we will show that if two paths are homotopic, then the indices are same. Okay, so if gamma 1 and gamma 2 are homotopic, we want to show that indices are same. So we will use this observation in order to do that. So if indices are same, what is the meaning of indices are same? Maybe I did not introduce that word. If index of alpha with respect to gamma 1 is equal to index of alpha with respect to gamma 2, for every alpha outside omega, that is the definition of gamma 1 and gamma 2 being homologous. Gamma 1 and gamma 2 being homologous. So what we are going to show in the next class is that if gamma 1 and gamma 2 are homotopic, then gamma 1 and gamma 2 are homologous. The converse need not be true. Homotopic implies homologous. And in order to show that, we will make use of this observation. So let's prove this observation. If alpha is, first observation is, so proof is starting here. Okay, so I don't always write proof is starting, etc. This is the claim and this is a proof. Note that alpha is outside gamma 1 star, alpha is also outside gamma 2 star. Do you see this? Alpha is outside gamma 1 star because if alpha belongs to gamma 1 star, then for some s this is 0. But modulus of a quantity cannot be strictly less than 0. Therefore, alpha is outside gamma 1 star is clear. Alpha is also outside gamma 2 star because if alpha is gamma 2 s for some s, then for that s you are getting alpha minus gamma 1 s is strictly less than alpha minus gamma 1 s. But something cannot be strictly less than that itself. So alpha is also outside gamma 2 star. So this is true. And therefore you can define, because alpha is outside gamma 1 star, this makes sense. Alpha is outside gamma 1 star, so that I can put in the denominator. Alpha is also outside gamma 2 star, which I am yet to use. So I'm going to define gamma to be gamma 2 minus alpha by gamma 1 minus alpha and then make this observation. What is gamma prime by gamma? So just do the derivative and divide by gamma. You can check. It will be of the form gamma 2 prime by gamma 2 minus alpha minus gamma 1 prime by gamma 1 minus alpha. And this makes sense because alpha is outside gamma 2 also. So whatever you do to reach here is all okay. So gamma prime by gamma is this. And you can also observe that modulus of 1 minus gamma is strictly less than 1. Why is that? Just do it. 1 minus gamma will be gamma 1 minus gamma 2 by gamma 1 minus alpha, but that was our assumption. That is strictly less than 1. So our assumption is that mod 1 minus gamma is strictly less than 1. In other words, gamma star, the image of gamma is contained in the open disk D11. Center at 1, radius 1, right? It's in the open part of it. It's in the open disk. And therefore, index of 0 with respect to gamma is 0, right? Because gamma star is contained in this open disk. This open disk is center is 1, radius is 1. So 0 is just outside. Center is 1, radius is 1. So it is touching 0. 0 is a limit point, but 0 is not there. Therefore, the index of 0 with respect to this particular gamma that I have defined is 0. Index of 0 with respect to gamma is 0. What does that mean? So 0 is index of 0 with respect to gamma is index gamma dz by z minus 0. So it is just this. And what is the meaning of this? That is integral 0 to 1 gamma prime dt by gamma t. But gamma prime by gamma, you know, it is gamma 2 prime by gamma 2 minus alpha minus gamma 1 prime by gamma 1 minus alpha. So it is integral 0 to 1 gamma 2 prime t dt by gamma 2 t minus alpha minus this gamma 1 prime t dt by gamma 1 t minus alpha. But that is nothing but index of alpha with respect to gamma 2 minus index of alpha with respect to gamma 1, and that proves the result. Okay, so if that technical condition is satisfied, then the indices are same. For that alpha with respect to gamma 1 and gamma 2, and this we are going to use next time to show that if two paths are homotopic, then they are homologous. Homotopy implies homology. Okay, so we will do that next time. So we will stop recording, and we don't have so much time, but we have 10-15 minutes we can discuss. So let me stop this recording.